and talk about what you just found in this activity. We'll summarize it a little bit. I just want to go back to the opening. Today we're starting exponential functions, and exponential and log functions are the last types of functions we're really going to look at in the class. And we're going to stop in 40 minutes because Caitlin and I are switching classes for student evaluations. And I've handed back the quizzes. You either got them on Friday right after you took it, or I put them in your folders today. But just to remember, every time just before we have a test, the last material on that test, that particular class, remember, you don't get a whole week to do the homework. That always happens just before every test. So these next 3 classes, today is class 34, right? And Wednesday's class 35. So this homework will be due next Wednesday, which is December 4th. And then Monday's class is class 36, and that's the last class before our 3rd exam. That homework will also be due on the same day, the December 4th. So just like it's worked for all the other tests, there's always that one class that you don't have a week or 2 or 3 days to do the homework. So I just wanted to point that out so that when you come back from Thanksgiving, you'll keep an eye on it. The other thing is, you know how we always have those like chapter 1 test ungraded, and I give you a bunch of problems, and chapter 2 test ungraded. Caitlin over the weekend put in chapter 3 test ungraded. So if you want to start doing a little studying, in advance, like after Thanksgiving's over and you're all full up and you've had a lot of football or whatever you do for Thanksgiving, then you want to just try to go back and start reviewing some of the earlier material for chapter 3. You could try some of those problems. Okay, your last hourly test or semester test is going to be Friday, December 6th. That's why I'm telling you all this now, so that you can prepare a little bit. Okay. So let's do our little summary here. We came up with these 2 models for our rabbit population. The first model you looked at was a linear model. Notice where I put the y-intercept. This is a typical way of writing linear equations when you look at it from a statistics point of view. You always start with your starting value, which we call the y-intercept, or b in our algebraic model. We start with 1,000, so that first 1,000 in our linear model represents the initial population of rabbits. The initial population, 1,000 rabbits. Okay. Remember, initial means when time equals 0. When t equals 0, this second term disappears, and we just get r of 0 is 1,000. So the initial population is 1,000. What does the 1,000 mean in the exponential model? What does it mean here? 1,000, the first 1,000. That's a factor, not a term anymore. What does that factor 1,000 mean in the exponential model? It means the same thing, right? This is your initial population of rabbits. $1,000 rabbits. But notice, if we put in 0 now for t, we'd have 1,000 times 2 to the 0. 2 to the 0 is 1. So that's how we get our initial population of 1,000. Okay. So if I had started off with 50,000 rabbits, there'd be a 50,000 out in front multiplying 2 to the t. And in our linear model, it would be 50,000 plus 1,000 t. So that's the first 1,000 we see. What's the effect of the second 1,000? That's this 1,000 right here in our linear model. What's the effect of that 1,000? What does that 1,000, that second 1,000 do in the linear model? It's the what? It's the yearly population increase, right? So it's the Yearly population increase. So it's the rate of increase, right, in your population as your time increases by 1 unit, increments by 1 unit. So it's 1,000, it's a constant rate, 1,000 rabbits per 1 year, right? It's a constant rate. It's an additive effect. You're adding the same number from each year to the next, 1,000 plus 1,000 plus 1,000 plus 1,000. So it has an additive, it's an additive effect of adding 1,000 every year. Okay, what about the rabbit population? Oh, we already talked about that. Okay, second one. What's the effect of the 2 right here in our exponential model? What does that 2 do as we increase from 1 year to the next? Adam? So the effect of 2 in the exponential model is a doubling effect. And so what happens in successive years as t increments by 1, our rabbit population doubles. Okay, so here we have a constant also, just like we do in the linear model, but it's not an additive effect, it's a multiplicative. It's a constant multiplier, if you want to think of it, of 2. Okay, you double. It's a multiplicative effect versus an additive effect. Constant factor or multiplier of 2. It's doubling. Okay, so if we were to investigate what's happening now, we've spent a lot of time talking in the past, not only in this class, but in your other math classes, of linear growth and linear models. So we're going to focus today on exponential growth and exponential models. So here's an example of what we just looked at. Here's a graph of 1,000 times 2 to the t. Okay, and I've added this to, you don't have this in your notes right here, so you're going to have to do the old-fashioned note-taking like you used to do in math class, where you have to write it in yourself. I added that to the lecture notes. So anytime you look at any exponential function and you're trying to get a sense of what its equation is, these are 2 key points to look at. This particular function, if I asked you, how does P of t, if I tell you that P of t is a transformation of its parent function, let's say the parent function looks like this. Here's our parent function. F of t is 2 to the t. That's our basic doubling function right here, 2 to the t. And here's the one we just looked at with the rabbits. What type of transformation has happened to 2 to the t with our rabbit function versus just our regular parent function? What kind of transformation has happened? 1,000 times, oops, that almost looks like 2 times t, doesn't it? Let me make that t where it belongs, upstairs. Up there, there we go. So what kind of transformation is that from f of t to p of t? A vertical stretch by a factor of 1,000, right? So this function here is a transformation of our parent function 2 to the t by a factor of 1,000. So if you notice the 2 key points, if I didn't tell you what the equation was for this function, you could start off by putting some type of function notation down, and you would look at your y-intercept, which is when t is 0, what's the value of p? It's 1,000. So you know that if you were putting this into some type of exponential form like this, you would say, okay, when t is 0, my population is 1,000. So notice the minute you solve for this point, you get your value of a, because this b of 0 is just 1. So that always will tell you the coefficient or your vertical stretch or shrink. It will always tell you the number that's out front. So this 1,000 goes directly in front right here We don't know yet what our base is. We do because we just did the problem. But in general, we'd have to write this, b to the t. Now let's figure out what the base is. We know it's 2 from the work we've just done, but let's see if we didn't know. So that's where your next point comes in. So this 0, 1,000, that 1,000 will always tell us this coefficient right here. And then when we go to 1, we're at 2,000. So now we say when t is 1, we put 1 in here, we have 1,000 times b to the 1, and p of 1 is 2,000. So if you're solving for b, you divide both sides by 1,000, and there's your growth factor. There's your base for your exponent too. So now you have all the information you need. You know that this function looks like this, 2 to the t. So again, when you increment by 1 and you're trying to find the value of your base, you just take this number, 2,000, and divide it by that previous population, 1,000, and that gives you your constant multiplier. Just like when you go on a linear function, when the change in x is 1, you look at the difference in your y values. The same is true here, right? 2,000 is to 1,000 as 2 is to 1. And that gives you your base right there. And for this particular function, that's how you write it. Okay? So that's how you can come up with an exponential function from looking at its graph. So what's the horizontal asymptote here? What's the horizontal asymptote? What number are we approaching as t gets really, really small? 0. So we have the x-axis is the same. It's a horizontal asymptote, and we know that the equation for that is y equals 0. Okay, so in general, when you have an exponential function where the base of your exponential function is a number bigger than 1, as your x value or t value in this case approaches infinity, your graph rises very rapidly. It also grows without bound, approaches positive infinity. And as t, as a mathematical statement, not with the rabbits, but as t or x goes towards negative infinity, the values of this function get closer and closer and closer to 0. Can I ever have 0? Can I solve this equation and get 0 out here? Is it possible? Is this possible to get 0? You say no, why not, Shane? Because of what? The y-intercept is when t is 0, that's right here. Why can't the value of my function ever be 0? Well, let's divide both sides by 1,000. And if we do that, we get 0 equals 2 to the t. So if I'm trying to simplify this, there's an equivalent equation. If I divide both sides by 1,000, I get that. So can 2 to the t ever be 0? No, because no matter what number you put in for t, you'll always get a number out. There's no way to make that 0 because it's 2 raised to a power, even when it's a negative value and you're looking at the reciprocal. So in other words, if you look at, say, 2 to the negative 2, that's not 0, that's 1/4. So that's not 0. If you look at 2 to the negative 10, that's 1 over 2 to the 10th. I agree, that's a really small number. It's getting closer to 0. There's no way it will ever equal 0. All right, so let's take a look at the definition of your parent exponential function. This is your parent. Notice you have some number raised to your input, b to the x. So this is what makes exponential functions different from all the other functions you've looked at. Now your input value is the exponent. It's no longer down here like in a polynomial. You're used to raising x to a power. You're not used to x being the power itself. Notice here in our parent exponential function, the coefficient out front of b to the x is 1. So we say that when we define an exponential function, we say b has to be greater than 0. It can't be a negative value, and that b cannot equal 1. And so why do we have these restrictions? Well, let's take a look at 1 to the x. Let's do a little table. X, and here's f of x. Well, when x is 0, 1 to the 0 is 1. When x is 1, 1 to the 1 is 1. When x is 2, 1 squared is 1. When x is 3, 1 cubed is 1. When x is negative 1, we get 1. When x is negative anything, we get 1. When x is positive anything, we get 1. Very boring function. It's just your constant function, y equals 1. So that certainly doesn't have exponential behavior that we just looked at. Okay, so that's why b cannot be equal to 1. Why can't b be a negative number, for example? Well, remember here on your exponential functions you just looked at here a minute ago, what was your domain here? What's the domain? What's the values of x that I can put into my function here? Everything, right? All real numbers. Domain's all real numbers. We write that negative infinity to infinity with parentheses. So if we allowed a negative number in there, and we, for example, let's suppose we try to look at negative 2 raised to a power. And let's suppose we let x be, say, 1/2. Then what would we be looking at? We'd be looking at the square root of negative 2. And the square root of negative 2 is not a real number. So because our domain is all real numbers, if we actually allowed our base to be negative, we'd be getting values that were not real. So for exponential functions, and also if you tried graphing it, you'd have, for different values of x, you'd have a point above the x-axis and below the x-axis. It would be like an oscillating type of function. So we just say exponential functions have this form: b is greater than 0 and b can't be 1. Okay? B can be a fraction, like 1/2 or 1/3 or 1/4, 1/10, but it can't be negative. All right, so let's take a look at two different exponential functions. And these sort of generalize the types of exponential functions you can have, the basic parent functions. You can have a parent function where your base is a number bigger than 1, like 2 to the x, the doubling function. You can also have a function where your base is between 0 and 1, like 1/2 to the x. Now, there's interesting relationships between these two functions, and we'll take a look at those in a minute. But we call this first function a growth function because as x gets bigger and bigger, so doesn't the value of your function. It's called a growth function. Okay, where b is the growth factor. Notice that language, factor. That's that constant multiplier we talked about earlier. So when b is 2, everything doubles as you increment x by 1. If this was 3 to the x, everything would what as we incremented x by 1? Triple, right? Okay, so b equals 2 here. Everything increases by a factor of 2. A factor of 2 is just like doubling. Now with this second function, notice our behavior is very different. As x gets bigger and bigger, our function value is decreasing. As x gets smaller and smaller, our function value is increasing, so it's rising. So here our end behavior is just the opposite. As x approaches negative infinity, g of x approaches infinity. So it rises. And as x approaches positive infinity, g of x approaches the x-axis, but now it's the positive side of the x-axis. So here f of x is just the opposite. As x approached infinity, f of x approaches infinity. As x approaches negative infinity, f of x approaches 0, the negative side of the x-axis. So we call the first situation a growth function. We call this a decay function. Okay. So if I wanted to put g of x into a form where it had 2 as the base instead of 1/2, what would be my power? I can't say g of x equals 2 to the x because 1/2 to the x isn't the same as 2 to the x. What's the relationship between the number 2 and the number 1/2? They're reciprocals. So I could write it like this, 2 to the negative 1 to the x power, because 2 to the negative 1 means 1 over 2, 1/2. And remember, our exponent properties say that when we multiply, when we have a power raised to a power, we multiply our exponents. Okay, so 1/2 to the x can be written as 2 to the negative x. So what's the relationship between 2 to the negative x and 2 to the positive x? Or 2 to the x? Well, to get from here to here, I would put negative x in for my input. So my function f of x is 2 to the x. When I put in the opposite of x, I get this, which is 1/2 to the x. So this says if I take my original function, f of x equals 2 to the x, and I put in negative x for my input, and I get 2 to the negative x, then I've reflected this over the y-axis. So g of x is the reflection of f of x over the y-axis, and vice versa. I can say that f of x is the reflection of g of x over the y-axis. So these are reflections of each other over the y-axis. So you can see that here with two different colors. If I let f of x equal 2 to the x be my red function, and g of x equals 1/2 to the x be my black graphed function, on the same set of axes, then we can talk about one being the reflection of the other. So notice if I took this point right here, I reflect it over. So these are reflections of each other. Either way you want to go. Okay. So the reflections over the y-axis. So f of x and g of x have been reflected across the y-axis. Two different functions that are reflections of each other. So if I took f of x and I said f of x was 4 to the x, and I graph that, I get a nice graph of 4 to the x, then I know what, and I now do this, g of x equals 4 to the negative x, which is 1 over 4 to the x. I now know what this function looks like without having to graph all the points, because I just take 4 to the x and I flip it, I fold it right over the x-axis, excuse me, the y-axis, and I get 1/4 to the x. So that's the relationship between the functions that have a natural number here, like 2, 3, 4, 5, and then you take its reciprocal. They're just reflected over the y-axis. And one is growth, one is decay. Now I've added some stuff in here compared to what you have on your lecture notes, but I'm just going to keep this exactly the same as what you have on your lecture notes. So you don't have all this stuff here. You just have end behavior. I'm going to take all this out. You don't have any of this stuff here. We'll do it just like your lecture notes say. So if we're looking at the properties of exponential functions, whether they're growth functions or decay functions, Adam's already told us that the domain is all real numbers. So that's in some ways one thing that they have in common with polynomial functions, because the domains for polynomial functions are all real numbers as well. But that's sort of where any comparison sort of stops. What's the range? Can someone help me out with the range if I started looking at all the possible outputs for either the red function or the black function here? What would be the range in interval notation? What would be the range? Smallest to largest value in interval notation. 0, infinity, and then what do I use for parentheses? Right, because we can't be 0. So we go 0 to infinity. So we're non-negative. Our range is non-negative, all non-negative numbers. Okay. So our input is all real numbers. all real numbers. And our output is all non-negative. Okay, are these functions individually, if you were to look at if you could imagine just the red graph or the black graph, are they one-to-one functions? Yes, and how do we test for one-to-one? Does anybody remember the test we do to see if something's one-to-one? We have a visual test for one-to-one. That's to test a vertical line test if something's a function. So what's the only one left, Jane? Horizontal. So if we're just focusing on, say, the red graph, and I draw beautiful straight horizontal lines, you can tell these are beautiful straight horizontal lines. Through that graph, notice it only hits my red graph in one spot. So, and the same would be true for the 1/2 raised to the x power. So they're definitely one-to-one. So when they're one-to-one, what does that tell you about the function? If a function is one-to-one, what important information does that give you? It's a really big idea. We spent 2 days on it. Function will give you the same value twice. Almost. I think I know what you're trying to say. You come back to that same value if you do what? What brings you back to the same value? What kind of functions bring you right back to x? Inverses, right. So when you're one-to-one, this tells you it has an inverse function, right? And tomorrow, not tomorrow, Wednesday, we're going to look at the inverse of the exponential function. Oh, I can't wait. Yay, okay. Extrema, does this have any turning points? Either one of these functions? The red function or the blue function? Excuse me, the black function, any turning points here? Let's start with the red function. Does it turn around, change direction? Nope, it's always increasing. This is always increasing. That's another way you know whether something has a function or not. If you're always increasing or if you're an always decreasing function, you're definitely going to be one-to-one in both of those situations. So you know you have an inverse function. So no extrema. Our y-intercept is 0, 1. We have no x-intercept. The asymptote is the x-axis, which we write as y equals 0. Y, Linda? Y equals 0. So let's talk about our end behavior again. For the red function, our end behavior is as x goes towards infinity, f of x also goes towards infinity. And as x goes towards negative infinity, f of x goes towards 0. Our black function, which was our decay function, as x goes towards infinity, f of x got really close to the x-axis, so f of x approached 0. And as x decreased without bound, our function, oops, I should call that g of x, our function increased without bound. Okay. So that's the behavior of these exponential functions. So just like we did with rational functions and polynomial functions, we can look at, and this is why we spent 3 days on transformations, is because you can now look at transformations of exponential functions. But before we do that, I've given you an exponential function, a parent function here, but I haven't told you what function this is. Is it, first of all, do you know whether b is greater than 1 or between 0 and 1? What do you know about b before you even start? It's always increasing. It's an always increasing function. So what does that tell you about the value of b? It's bigger than 1. So we know b is going to be bigger than 1. Okay? So find those two key points that I mentioned to you a minute ago. Look at your notes and see if you can come up with the function for this particular graph. Here? Okay, so someone want to tell us how we approach trying to find the graph for this exponential function? What you look for? What 2 points you look at? Excuse me? Okay, so you want to look at when x is 0. You look right there. When x is 0, your output value, f of 0, is 1, which tells you that you have a 1 out in front. Okay, I've already told you it was of that form right here anyway. But in general, you may not know whether it's going to have a number multiplying it on the outside. You won't know, like on a test, whether it has this form or whether it has this form, a b to the x. So that's always the first test you want to do. Does it go through 0, 1? And if it does, then you know it looks like something like this. Now, how do you figure out the b value? Some other table other than Adam that figured that out? When x is 1, your output is 5, right? So if you didn't know how to then figure out that it's 5 to the x, you could go back to your basic formula. And just like you always do, you plug in the point that you know. You know that when x is 1, your output value, f of 1, is 5. So that tells you b is equal to 5. So here is your function, 5 to the x. Any questions on that? Then the ratio here is 5 to 1. So just to test it, go out to the next point, increment by 1. You go up to 25. And notice 25 is 5 to the second power. 25 divided by 5 is 5 to 1. 5 divided by 1 is 5 to 1. So you have that constant multiplier, that constant growth factor of 5. Okay. All right. Now let's take a look at a transformation. We don't know what our parent function is here. We don't know what our base function is. We're performing some kind of transformation. Okay? Whatever b to the x look like, we know our original b to the x would go through 0, 1, and our horizontal asymptote would be the x-axis. So if you compare, and I don't know I don't know what number it goes through when x is 1, because I don't know my original function. But if you just looked at this, what kind of transformation has happened between how you know a beginning exponential function between, say, negative infinity and 0x, and what this function is acting like? What's the horizontal asymptote for this function? 3. Okay, so it's approaching 3, so it's got this horizontal asymptote here. Okay, so it went from being at 0 and it's moved up to 3. Right? And if you look at this point, you're at 0, 1, and now your y-intercept is 0, 4. So it's shifted up 3. Okay? So what could that be? What kind of transformation might that be? Vertical. So we know it's some kind of vertical transformation. And the question is it a shift up 3 units or a stretch? And how do you tell the difference between stretches and shifts? How do you know whether this is a stretch or a shift? Well, when we stretch a function, we're still going to keep our same asymptote, horizontal asymptote, but notice this entire function just got moved up the whole y-axis, right? Every single y value just got bigger by 3. So this is a shift, a vertical shift by 3 units. Okay, so we know this. We know our new function, g of x, is going to be b to the x plus 3. We're going to do a vertical shift. Now we got to figure out b. Okay, so let's take a look at 1. 1 is 1 comma 5. So to go back, I subtract 3, right, to go back to it. So if I subtract 3 from that, I'd be at 1, 2. So I am 2 to the x plus 3. Because 1, 2 just went up to 1, 5. All my y values increased by 3. All right, now I look at my next function. I'm trying to figure out what kind of transformation it has. Notice my horizontal asymptote hasn't changed, but I'm no longer going through 0, 1. I'm going through 0, 3. So I've done some kind of vertical movement, but it's not an entire shift up because I have my same horizontal asymptote. So this must be a vertical stretch by a factor of 3. So we have g of x here is 3 times b to the x. Okay, now how do I figure out what b is? Well, take another, that very important point, 1, 1, 6. We're at 1, 6. So when x is 1, your output is 6. So just throw that in now and solve for b. We put the 6 here, that's our y value. Our x value is 1. So this says 6 equals 3 times b. So b equals 2. So this is a vertical stretch of a doubling function 2 to the x. It's a vertical stretch by a factor of 3. Okay. Vertical stretch by factor of 3. Okay, so you'll have some homework problems like that where they're asking you to try to figure out what type of transformation has happened to your original function b to the x. Okay, and those are the types of things you look for. All right, now we get to a very interesting number in mathematics. In fact, it's so special, it has a letter that represents it. It's called the number e. And E is used for the mathematician Euler, E-U-L-E-R. His name is, yay, Euler. That's who you're trying to remember, okay? No? Oh, what were you trying to remember? Yeah. Oh, yeah, who was that? Galois? G-A-L-O-I-S, okay. You've been trying to remember him for like a week, right? Yeah, now you've got it. Okay, good. So the number e is defined as the value that this expression, 1 plus 1 over n, the whole thing raised to the n power, as x gets larger and larger and larger. So let's investigate the value of e. We don't know what the value of e is yet by putting it into our calculator. So let's put this expression into our calculator and see what happens for these different values of x. So, oops. I turn my function on, I go to y equals, I clear everything out. So I'm going to use parentheses, 1 plus 1 divided by x, close my parentheses, then raise that whole thing to the x power. Okay, so before you do anything, folks, let's think about this for a second. If I put 10 in here for x, what am I going to get? 1 plus 1/10 raised to the 10th power. So that's 1.1 raised to the 10th power. Okay, let's just see what that is. Let's use our table to help us out here. So we set our table. We're going to start with 10. And make sure you come down here and hit ask, because we want to put our values in. We don't want it incrementing by 1 or whatever. So now go to the second table. And let's clear this all out. At 10, what are we? At 10, we are the number 2.5937. Okay, 2.5937. Please don't put in the next number. I want to ask you. What do you think's going to, oops, that goes on under 10, not, that goes in under here. 2.5937. Okay, try to stop your fingers for a minute. What do you think's going to happen as x gets bigger and bigger and bigger? What do you think is going to happen to this, the value of this expression, 1 plus 1 over x to the x power? So our exponent's going to become 100, 1,000, 10,000. Think this is going to grow without bound? Okay, so the fraction inside is getting really small, but our power is getting really big. What happens if you take a fraction to a power? Fraction gets smaller and smaller, you're adding it to 1. Does that make sense? Or do you think this is going to just get much bigger? Anybody have an intuitive feel? All right, let's try it then. If there's no intuition, we'll have to rely on our calculator. So let's put 100 in. And what do we get for 100? 2.7 2.7048, 2.7048. Well, we got a little bit bigger, but not much. Let's put 1,000 in. See what happens. 1,000. 2.7169. How about 10,000? Ooh, not much bigger. Only way out, what, about 12? Right? 12 in the what place? Not the tenths, not the hundredths. 12. Do you know your decimals? I'll let you figure that out then. 181. So if you keep playing this game, you make x bigger and bigger and bigger, it's going to approach the number e, which is approximately 2.7182 if we rounded it to 4 places. So that's the number that this approaches. It's this expression, if you were to graph this, this would be like the horizontal asymptote, 2.7182. So if you graph this function and let x get really big, this number is not going to get beyond the number e. So if you were to graph e to the x, it's an exponential function, and it's going to be, since e is 2.7182 to the x power, it's got to be a graph between 2 to the x and 3 to the x, because the number 2.7182, at least as an approximation, this is approximately, right? That's got to be between 2 to the x and 3 to the x. So if you go on here, you see you're at 0, 1, and at 1, look where you are. You're just a little bit below 3, blah, 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 and a little bit bigger than 2.5. So this really is 1 comma e. The exponential function plays such an important role in, with the base e, that not only does it get a special letter, but you'll see that in lots of our applications, it's going to give us a special formula, especially like with money growth and many other applications. But for compound interest, this we use this base quite a bit. It's called the natural base. So here's 4 exponential functions that have had transformations, and I just want you to put the letter of the graph beside the number here. So the parent function is this really light graph here, and the transformation is the heavy. Do that for homework, because I have to go get Caitlin, because she was supposed to be in here 5 minutes ago so you could do the student evaluations. So do this for homework for Wednesday. Please come in Wednesday with